Checking into lab this afternoon. Lab instructions in your lab manual. We'll meet upstairs. After we check in, we'll go downstairs for lecture.
Do we have to have our safety glasses and lab coats to check in, or can we just?
Please read the directions for checking in. Everything is there. Okay, where did we leave off at? Pocklopyridine. There was a question before that. Product of this reaction here. Phosphoric acid is a strong enough acid to do acid catalyzed chemistry, similar to sulfuric acid. Anybody got a product here? Can you name your product? Can you name that product? One phenyl, one butene, E. Does that look right? Is that the name of your answer there? Yeah? Everybody agree? Is that the name? Yeah? I think that's the name, right? Yeah? Okay, everybody good? Okay, make sure you're good. Pocklopyridine. What type of mechanism did we do up here? E1, right? E1 always gives what type of product? States F, most stable. Yeah? Okay. All right. Questions about that one? Okay. All right. Let me know if you have any questions about that one. Pocklopyridine. Pocklopyridine is a, what are we under? B? What is A and B? Dehydration of alcohols. Another way to dehydrate an alcohol, particularly for a primary alcohol. Pockle. Bonding for phosphorus. Everybody good with bonding for phosphorus? Yeah? Expanded octet. Okay, little structure there, lone pairs everywhere. Okay. This attacks the phosphorus. What do we do when we attack the phosphorus? We break the weaker bond. High bond is broken away from phosphorus. And that gives, I'll just call that R. Oxygen. Oxygen is now bonded to phosphorus. Electrons up onto oxygen. Minus. Chlorine, chlorine, and chlorine. H here. Oxygen is now positive. We're going to have to come back and show this carbon later. Okay. Then electrons back down, and we can kick off one of the chlorines. Or is this a better leaving group? Permeated oxygen. Might be a better leaving group here. But if we kicked it off, where would we go back to?
Just our beginning product.
We just go backwards. That's an equilibrium there. Okay. We could kick that off. Also, we have pyridine. We could take care of the H. If we remove the H, then that would no longer be a good leaving group. And then certainly the chlorine would be kicked off. Chloride is a good leaving group. What does that give? Reform the double bond and two chlorines, positive. This is our third time we've seen it. We did nucleophilic addition, elimination, right? Here we're attacking the phosphorus. We got to take care of the proton. Let's go ahead and take care of the proton. What can take the H and let this oxygen go neutral? Yes, Cl minus could, but we have a base present. Pyridine. I could have taken it there, like I said. If I had taken it there, then when this comes back down, the chloride is certainly the only leaving group. But we can take care of the proton here, acid-base reaction. Do this. And that leads to what? I'm going to put my carbons back in. Oxygen. Leads to that. Right? Lone pairs back. And the pyridine is now protonated. Right? Everybody rushing to write this down, or are you maybe going to rewatch the video and then get your details? Okay, it is video, yeah? Now the nitrogen is protonated, and we got that in a Cl minus. So we got balanced charges. But this right here is a dichlorophosphate ester. How did we get there? We started with a chlorine under my hand, Paco. Now the oxygen is under there, a substitution reaction. What type of mechanism? An additional elimination. That's how we got the oxygen on there. Not SN1 or SN2. But we also had to take care of the proton. And we'll have to take care of the proton throughout the course. Okay? And you'll hear me say we got to take care of the proton. Somehow. Alright? But this is a lot like a tosylate. The oxygen and tosylates bind to a sulfur with oxygens, and so a lot of pulling here. These greedy atoms pulling electrons. It makes that whole thing a good leaving group. Now another pyridine will actually do an E2. Pyridine, I'm not going to redraw the other pyridine. Second pyridine, I'll use this one. So, okay. Another pyridine comes in, takes the H, these electrons move in here, these get kicked off. What type of mechanism does that look like? I just said it, E2, right? E2. And what does that give? What is my, gives this, right? E2 elimination. You might ask, is pyridine strong enough to do an E2? It's borderline. In this case, I'm showing it doing an E2. So slightly basic nitrogen. Great leaving group that. Now this to a tosylate. Okay? And this method works better for dehydrating primary alcohols. Because if you dehydrate an alcohol with sulfuric acid, what mechanism is that? E1, and E1 proceeds by a carbocation. And are you going to make a carbocation here? Very unlikely, very difficult. Okay? Aquapyridine is a method for dehydrating primary alcohols. Okay, better. Tertiary alcohols dehydrate very easily with just sulfuric acid. Secondary is in between. Okay? Aquapyridine. Reactions over here. Okay? Alcohols, aquapyridine, show products. Since it's an E2, what do you remember about the E2 requirements?
Inversion of stereochemistry.
No, it's SN2. E2, what is E2? Some requirements there. Strong base, we said pyridine is apparently a strong enough base. Pyridine's not super strong, but what were requirements for the mechanism?
Your hydrogen has to be anticoplanar to
Yes,
your
yes. We're doing an E2 here. So you have to keep that in mind. We did examples in Organic 1, review, okay? The H and the leaving group need to be anticoplanar. You guys did that with Dr. Agee, okay? All right. There's some examples to work. Anybody already worked those? What'd you get?
I got Sasef product for the first one and Hoffman for the second one. Where
Okay.
you have the double bond between the OH and the methyl up top. Only the OH is gone. And then double bond
Well, let's look at them next time. Good, good. Ethers. How do we make ethers? Common way to make ethers is a Williamson ether synthesis. We saw this in Organic 1. Okay, we'll be using SN2. It involves forming the alkoxide. And as we saw in Organic 1, these can be made, the alcohol can be converted to the alkoxide. Common way is using sodium metal. Okay? What's the charge of the sodium here?
0.
0. It's metal, sodium metal. Okay? 0. Metallic sodium. Anybody ever cut sodium in the lab? It's a soft metal. You can cut it with a knife. No? We didn't do that in Organic 1.
You showed us what they were in the lab one time.
Yeah, I don't think we did this past fall though. Yeah. Lab next week is Williamson ether synthesis of acetaminophen. I think there's a reflux period. During the reflux, we might cut some sodium. Okay. This is a redox reaction, right? It's not a traditional acid-base mechanism. Fate of the H, we produce hydrogen gas. Okay, this is not balanced. If you want to balance it, you're welcome to balance it. Okay, you got to have 2 of these in order to make hydrogen gas, right? This is just sort of commonly away. We know that's ionic, right? We know that's O- and sodium plus. Okay, and an O- we call an oxide, but when there's an alkyl group on it, we call it an alkoxide, right? So we made the alkoxide. Another way is sodium hydride. This is a traditional acid-base reaction because this is sodium plus H minus. You can't have H minus. And H minus is acts as a base, and we can show a traditional acid-base mechanism. These electrons take the H, these stay behind. What are we forming right there? H2. But when these stay behind, we have the O minus, right? And where's the sodium going to sit? With the O minus. Okay? Again, up here, this is redox, and we're not going to be able to show a traditional aero mechanism for a redox reaction. It's not as easily. It's probably a radical reaction. 2 common ways to make alkoxides. So we can do chemistry now. Now this, what does sodium do to this? Right? What does it do? It converts it to the alkoxide, right? Can I just do that? That's what sodium does, right? That's the product after sodium. And then what can this do when we put in this? What's the reason for generating these?
So you can
Make it a good nucleophile. We're base, but we're doing nucleophile chemistry. Now the nucleophile can come in here and attack
Chlorine.
where?
Chlorine.
Tell me again.
Chlorine. Chlorine.
Okay, so I'm looking at her, but I'm hearing you. I'm like, okay. I don't know if you said anything. Tell me.
Chlorine.
Chlorine? Okay, because I can't hear.
Or the secondary.
Yeah. Attack here, kick off the leaving group, and what's going to be the product? Okay? Everybody good? Question?
Why it was the alpha cyclic bundle, two carbons away from the so like in the original, in the nuclear, in the original, the original flow, wasn't that only 3 carbons away?
Yes. I suppose you're thinking about the bromine should be here, right? Everybody good now? Yeah? I made a common mistake. That's why I made it, because very often I get answers where the things on the ring are not in the right place. Okay? The bromine is para to this group. Para is opposite. Okay? And it still is. I mean, if under my hand was a chlorine, that would be the thing on the line, right? Well, instead of a chlorine, it is now what? Oxygen. Oxygen replaced the chlorine. Okay? Of course, the oxygen has everything else bonded over here. What's this? Is my stereochemistry right? What's the exact same as that? Because I did not do any chemistry with this carbon. Okay? Yes. All we did was we made the good nucleophile, and then the good nucleophile displaced the chlorine from that carbon. We made that bond. What type of product did we make? Yes, an ether, right? Synthesis of ethers. Okay, so the alcohol converted to ether. Ether, this is a common sequence. This is called a Williamson ether synthesis. Did you guys see this in organic 1? Okay, we did as well, right? All right. Common way to make ethers. Apparently, chemists back in the 1800s, mid-1800s, Williamson did a lot of this and made ethers this way and said, hey, you can make ethers from alcohols. But you first have to convert it to a good nucleophile by some type of redox or acid-base chemistry. Because SN2 requires a strong nucleophile, right? Okay? Hold on, I thought bromine was a better leaving group. Is bromine a better leaving group than chlorine? Huh? So why didn't we kick off the bromine and attack this carbon? That's what?
It wouldn't be an ether if you went there, would it?
Yeah, it would be an ether.
If you stuck the oxygen.
I mean, why didn't we have the oxygen kick off the bromine and make,
Oh, okay.
Isn't that sp2?
why didn't we make that product?
That's sp2. It has to be sp2.
Right, because you don't, whenever we displace leaving groups, it has to be on a tetrahedral carbon. At least thus far. When we get to test 2, we'll do some other, we'll displace leaving groups from sp2 carbons, but it won't be by SN2, it'll be by a new mechanism. Yeah. You're not going to displace this by a traditional reaction that you know already. What do we call this carbon here? What type of carbon did we attack? Name for that carbon.
Alpha carbon. Allylic.
Not allylic. Allylic is a carbon next to an alkene. What do you call this carbon bonded to the benzene ring? Benzylate. Yeah. Which is also a great carbon to be attacking by SN2. Why? That's going to be much more reactive than just this. Why is that much more reactive than just that? There's no resonance here, there's no carbocation.
Does the phenol group pull some of the electron density away from those carbons?
Potentially, but that's sort of,
Making them more reactive?
yeah, because it's sp2 carbon is electron, yeah, potentially, but there was something bigger we talked about in organic one. I'll let you think about it, maybe I'll ask you again. But, a benzoyl chloride is much more reactive towards substitution than just a regular alkyl chloride. Okay, we covered that in organic one. Reaction below, phenols. Up here that we call it a phenol. No, that's a phenol. This is a phenol. OL, alcohol. Benzene is called a phenyl ring. Phenols are acidic enough to be deprotonated by hydroxide. Not a regular alcohol, but phenols, yes. Phenols pK have about 8 to 10, can be even more acidic than that. You can have phenols down to like 3 or 4, depending on what groups you have on the ring. Okay? Regular phenol is about 9 or 10. But hydroxide will deprotonate a regular phenol. These electrons take the H, these electrons stay behind, and we get the O minus, right? Sodium plus, and then what do we generate? Water, yeah? How do we know that this will take place? Remember how to judge equilibrium? 8 to 10. The acid over here is 8 to 10. Let's just call it 10. What's the acid over there? Water, what's its pKa?
16.
16. You got to be able to judge acid, okay? Do this type of stuff, assessing what's the acid. Which side's favored, 10 or 16?
16.
16, so you see how that's favored. It's favored by how much? 10 to the 6, which is, what, 1 million? So at equilibrium, you got 1 million of these in anion form and only 1 of these left. That's pretty much complete, because if you did a percentage, that's probably 99.9999% complete. That's pretty much complete. If you can get 99.999% of your, something to do something, you did a great job. You're pretty much complete, okay? But up there, it ain't going to be complete. You'll be 16 and 16. It'll be a 1-to-1 equilibrium, and in practice, that does not work. Phenols are more acidic. You can use a weaker, more standard base to deprotonate them. So do product down here. Pretty straightforward. Somebody got it? You confident in your stereochemistry? Yeah, I think so. Good. You did it a good way. Yeah. Uh-huh. Started with bowling, you ended up with bowling? How's that? You sure you did inversion? You want to do R and S real quick? Right there. What's the leaving group? Tosylate. We got 3 carbons with a leaving group on it, and the N carbon has a D. Here are 3 carbons. The N carbon has a D. Instead of a leaving group on the N carbon, we now have that oxygen. Okay? And this is SN2, and SN2 comes with inversion. Right? So that's why we have inversion. And what else would be formed here if we want to completely balance this out? There's 2 different steps, but if we completely balance it out, there's 2 other things formed here. What is water? What else would be formed here? The leaving group doesn't just disappear. It's still here, right? What is it? OTOS? What's the charge of OTOS? Negative. What plus sits here? Okay. Potassium tosylate, I reckon it is. Why didn't I show charges of potassium tosylate? Well, what if it was potassium chloride? Do I have to show charges of that? No, you know it's charged, right? That's kind of just written as kind of formula-like, right? It'd be the complete fate of everything. O minus, the leaving group left, but the K plus is K plus always. You're never going to, K plus is never going back to K metal unless you use electricity. All right, electrolysis. All right. Everybody good with inversion? We did one like that before. Because how does the nucleophile come in? The leaving group is in the plane that way, so how does the nucleophile come in? O minus. It comes in directly opposite, right? Kicks it off. So here's the carbon. Instead of the leaving group being like that, straight over like that, the new group is what? Straight over here, right? And so the nucleophile is straight over here. But these 2 groups just move that way to make room for it. So the D, instead of being here, sort of moves that way, but it's still forward. And this group up here sort of moves like this. You can draw this other bond however you want. I can draw it like that or like that. But it's like that. I mean, that's what I got over here. Or you can do R and S. Did you do R and S? Was it indeed inverted? Yeah. Yeah. Again, that only works 99% of the time. But just about every case, you can just do that. Yeah. Because this is what? RS. Yeah, that's S. And I bet you a steak dinner, that's R. Again, that only works if your nucleophile has the same priority as your leaving group, but 99% of the time it does. At least in the introductory level. Okay, in addition to hydroxide, you can also use other weaker bases such as carbonate. What's the formula for carbonate? Gym chem, right? Remember carbonate? CO3 2 minus. You can also use phosphate. What's the charge of phosphate? It's PO4 3 minus. And so if you had potassium phosphate, how many potassiums would you have with phosphate?
3.
Okay, 3PO4. But if you have potassium carbonate, how many potassiums would be with carbonate? 2. So it would be K2CO3. Okay? Now, these are also bases. You can show full structure. They're weaker bases. They're a little bit weaker than hydroxide, but you can also use these for phenols. You can't use these for alcohols. And in lab, our first lab next week, we'll be using these types. Okay? You actually have a choice. Okay? Okay, need to be able to go backwards. We did a touch of this in Organic 1 with me. Did you guys do retrosynthesis for Organic 1? Okay. What we're doing here. Here's some ethers. Can you provide a synthesis of each of these? A Williamson ether synthesis? Going backwards. That is, what type of compound do we want to start with? Williamson ether starts with a alcohol. Or phenol, yes. Yeah. A specialized type of alcohol. Starts with an alcohol or phenol, and then we alkylate it. And when you alkylate it, you need a carbon leaving group, right? So, you'd be able to do synthesis. I'll let you do those for homework and see how you're doing, so you can ask questions. Anybody have questions right now? Additional homework, explain why the Williamson ether synthesis below is not logical. Think about that one. Thioethers can also be made this way. Where's sulfur in the periodic table?
Right below oxygen.
Just below oxygen. Okay? Nobody look at the periodic table. Don't look. Okay? What's below sulfur? Oxygen, sulfur. It's a very important trace metal. You get it from eating lots of nuts, I think. Selenium. Se. Don't look. I saw you. What's below selenium? This one you don't see as much. Okay, what's below selenium? Periodic table. Tellurium. Okay, tellurium. I've done some work with some tellurium, selenium and tellurium compound. What's below tellurium? I think it's polonium, isn't it? Isn't it? Pio?
Yeah.
Polonium. Who discovered polonium? Polonium is radioactive. Marie Curie. And I believe she named it after Poland, right? Her homeland. Uh-huh. Okay, so there's that one. What's below nitrogen? Phosphorus. Okay, all right. So, thioethers, analogous to oxygen. Okay, you can have SH compounds like OH. Okay, they're smelly, and selenium and tellurium compounds can be very smelly. Good thing oxygen compounds are not. Imagine that. Water was smelly. I don't think planet Earth would have developed if water was smelly. But H2S, Huge difference between H2O and H2S, all right? But you can have such compounds that are important in biochemistry, okay? So that's why I kind of pointed out. But again, it's very similar chemistry. What's the base going to do? It's going to deprotonate it and make it S-. And then the S- will do what? Come in here and attack the carbon, kick off the chlorine, and we can make that bond. Okay? And I just have this cyano group over there. This is a reagent that I've used a lot. But, I mean, the cyano group's there just along for the ride. But it's just a Williamson ether synthesis using a sulfur compound instead of an oxygen compound. All right? Ethers, reactions of ethers. So we moved on from alcohols. We did some reactions of alcohols. Then we used alcohols to make ethers. Now we're going to do reactions of ethers. Well, ethers don't have a lot of reactivity. Not going to be much here. Ethers tend to be end products. Okay? And the one thing you can do with ethers is go back to alcohols. You can cleave them backwards. It's almost like a retro Williamson ether synthesis. Williamson ether synthesis, you start with an alcohol and you make an ether. Just about the only thing you can do with an ether is turn around and go back to the alcohol. But you also get another product because ultimately we are going to cleave it. Let's look at this. If you take this ether and heat it with HBr, you can cleave it. We'll break it apart. We will form an alcohol very often unless something strange is going on. Okay. So what's going to be the product? Well, I want to address this in terms of, well, what can we do here? We got this in HBr. What could be a first step in a mechanism? And we'll work our way towards a product. If you got a strong acid, usually the first thing you're going to do is protonate something. What do you want to protonate? Duh, the oxygen. It's the only thing you're going to do to protonate, right? We got H plus Br minus. Let's protonate it. By there, we got a Br minus. Okay. Ultimately, this oxygen can be a leaving group. How do you make oxygen a better leaving group? Protonated. It's now a leaving group. But we have a choice. Is it going to leave that carbon or this carbon? Which carbon is it going to leave? And which mechanism will it leave depending on the carbon? What do you want to do next? What can you propose? Micah? If it leaves the tertiary carbon, let's do that. And then we may come back into the other. We're going to leave the tertiary carbon. Can you do that? What if the oxygen just leaves? Is that a good leaving group? Yeah, we made it a good leaving. What would that give? It would give a carbocation, yeah, Micah? Plus what? Methanol. I'll draw that out. See, that just looks strange. It's like a line there. If I had another bond here, to me it looks more specific. So, I don't know. I would probably for us just say methanol. Okay? But, can I put an ME on the end? Does that look a little bit better? I mean, that is a methyl, right? Okay, so I kind of, yeah, it's going to make methanol. Hey, an alcohol. We just made, remember I told you going back to an alcohol? But is this reasonable to make a tertiary carbocation? Of course. What can happen to the carbocation? Yes, we got that Br minus floating around. And bam. And so that's going to give this. And there are two products. We actually went back to an alcohol plus an alkyl halide, which is sort of what you use to go that way. Don't you make the anion and then you get problems there, it's tertiary. Yes. Could we have done something else here though? Ultimately, we did chemistry over here at this carbon. Could we did chemistry here? What if this attacked here and kicked that off? I'm going to do A here, A here. That went A. What if we attack there Well, before we attack there, instead of the leaving group leaving this carbon, could it just leave that carbon and make cation over there? No. But could you do this? What would that do? That would be A. This would be the B root. What mechanism did we do with A? That was SN1. Because it was substitution. Under my hand is oxygen. Now under my hand is bromine. We substituted the oxygen for bromine. This is B. The B pathway is what type of mechanism I'm showing? SN2. And what would that give? That would give the leaving group, which would be that plus what? Methyl bromide. A bromine on a methyl. And that would be SN2. Which pathway is going to occur? First off, the answer is, in this case, both are almost just as likely. They're both reasonable. I'm going to give you some guidelines, though. Here's what we're going to do. When a tertiary reaction site is present, always go SN1. Because tertiary carbocations form so quickly. Okay? The A route is going to be faster here. Making a tertiary carbocation is going to be very easy and fast. Okay? And the other statement, if there's no tertiary site available, go SN2. Okay? So when we're doing this, we get to this point where we say, is there a tertiary site available? Yes. So what mechanism are we going to do? SN1. And so what would be the product of this based on the guideline? A. A. Okay? A here. Now the SN2 pathway is reasonable. This reaction may give a mixture of both the A and the B products. But for our purpose for this class, to give you some clarity, okay, I give you a kind of statement here. Now sometimes books will vary on this. Okay? Try the one below on your own. Okay? I'm going to ask you to do more and more on your own, and we'll look at them in class. There's another one below. Okay? There's several below. Work these as homework. We went through everything you need to know right here. But you got to make a choice. And when you make a choice, I gave you the guideline to go by. Okay? Ultimately, ether, this is about the only chemistry you can do with ethers, is cleave them back to the alcohol and the alkyl halide. Okay, using HX, like HBr, HI. Otherwise, ethers tend to be pretty unreactive, especially under non-acidic conditions. That is, let's get rid of double negative. Let's just call it basic conditions. Under basic conditions, ethers are almost unreactive. Because to make ether react, you first have to protonate that oxygen to make it become a leaving group. And if you're under basic conditions, you don't have any acid to do that. And if you don't protonate the oxygen, not much is going to happen at all. So ethers are pretty much inert under basic conditions. That's why ethers are used as solvents for highly basic reactions. Because ethers just don't react under those conditions. And so you have an inert liquid that can just be a solvent. Typically, you don't want your solvent reacting with anything. Okay? And what are some common ether solvents seen in the lab? I'm sure we've used at least one of these before, I think. It was also used during the Civil War as an anesthetic. Yeah, diethyl ether. Okay, almost looks like a bat flying. Okay, give it some eyes or something. Four eyes instead of two or one or something. Okay, diethyl ether, very low boiling. Okay, give you a headache if you drink too much of it. Okay, very common solvent. Another common solvent is a cyclic ether. Just a 5-membered ring, one oxygen in the ring. Anybody know the name of that? We've never used it. Have you ever seen or used it? Y'all use it in organic one? Okay. Or you just read my hand up. It's called tetrahydrofuran, THF. It's another common one. It's a little bit better solvent. The boiling point is higher, and so it doesn't evaporate. See, ether, you like use it for TLC, and before you even, it's like evaporated. You just can't work hard to work with. THF it has a little bit more soluble, it's a better solvent. The cyclic nature makes it a little bit more potent because it pulls back, the ring pulls it back and exposes those lone pairs a little bit more. Okay, guys. But at this point, we're going to be moving into epoxides. Okay? I gave you that handout already. See some of you in lab this afternoon upstairs at 2:30 for check-in. Instructions in your lab manual. Everybody good? Have a good day, guys.
I brought it with me.